Greetings, everyone. We are Profitality Labor Guru, an industrial engineering consulting firm specializing in improving unit economics. We apply our industrial engineering principles to the service industry and use a holistic approach to our problem solving. Under the Labor Guru banner, we focus on labor management solutions to find methods to optimize labor unique to the client, whereas under the Profitality banner, we focus on what we call optimizing the Ps. By optimizing the processes, procedures, platform, places, people, etc., we are able to optimize the facility to meet client goals. Ultimately, through optimized labor and optimized facility, we are ultimately optimizing the client investment. Our team is comprised of a young and energetic core of industrial and system engineers with advanced degrees ranging from Masters of Science to PhDs to Black Belts in Lean Six Sigma. Our senior staff has a cumulative experience that spans over 80 years in the service industry, mainly food service. Whether it's labor related or facility related, our differentiating proposition focuses on four main areas: advanced training degrees, mentioned previously, our ROI investment optimization focused approach to drive unit economics, to drive brand growth through crew-centric ergonomic designs, our experience with working with over 65% of the top 100 brands listed in National Restaurant News, and our significant industry involvement with over 100 thought-leading articles, seminars, and other industry involvement, such as tips posted on YouTube or publications about simulation in the Industrial Engineering magazine. With our crew-centric design, we aspire to keep team member satisfaction up while maintaining customer satisfaction high to increase sales, leading to increased profits, ultimately leading to grand growth. Welcome everyone to Profitality Labor Guru's presentation on drive-thru order management, tracking metrics for drive-thru optimization. I'm Carlos Espinosa, Director of Consulting for Profitality Labor Guru. Alongside me is the architect of the model you will see shortly, Victor Cerejo. In today's food service ever-evolving world, customer orders have been getting more customized and more complex, while their willingness to wait for orders seems to be diminishing. Restaurants are attempting their best to keep up with the influx of orders that are inundating their systems, knowing full well any kink in the system has major effects. In single-lane drive-thru systems, which comprise the majority of the drive-thru in food service, ensuring constant pace of flow is key in a successful drive-thru. But every operator has that one complex, low-moving menu item that is similar to throwing a wrench into the engine. It's not popular enough to streamline operations. Think of that one item that you have that has a long cook cycle that doesn't get ordered enough, but it is popular enough to stay on the menu. Handling these exceptions or these disruptors is paramount to ensuring bottlenecks are minimized and throughput is maximized. One method, which was once thought as taboo, as customers felt they were being sent to purgatory, has come back with a vengeance: parking procedures. Utilizing Simio, Profitality Labor Guru has created a model of a single-lane quick service restaurant to test and define optimal drive-thru design, which includes equipment layout, labor deployments, and assembly procedures. But we have also included a unique decision logic to model parking procedures as well. Additionally, we have added a key metric that has picked up traction in maximizing throughput in the drive-thru conversation, which is how often does the order beat the car to the window. The best-in-class drive-thru operators focus more on this metric versus total time spent in the drive-thru lane. The best-in-class operators will have that time be 10 minutes plus, but maintain their window time in the sub-30s, sub-20s, because they focus on beating the car to the window. Using decision trees and searches in the processes, this model determines changing outcomes based on the scenarios tested. We will be discussing how the model's core logic was created, such as order routing and process logic used to reroute the orders based on variable factors as the model runs, as well as gather unique data points that all restaurants should track in order to optimize their drive-thru operations. With that, I'll hand it over to Victor, again, the architect of the model, who's going to walk you through all this in a little bit more detail.
Thank you, Carlos. I've always wanted to be an architect. And hi, everyone. My name is Victor Cerejo, and I'm a senior engineering consultant at Profitality Labor Guru. For the last couple of years, Profitality Labor Guru has built Simio models for the food service industry. We use these Simio models to test different scenarios and experiments before restaurants commit to going live with these changes. Some of the typical changes we test include menu or product mix changes, since product mixes could differ from market to market, or facility layout changes, such as moving equipment to different locations in the kitchen to test the impact from the different outputs that will be analyzing. Doing this gives the restaurant concepts confidence when they plan to roll out these changes in their facility. We're excited to share with you today some of the order management strategies that we use in our model to facilitate these tests. So today we'll be covering an overview of the model, where things are stationed, and some of the framework of the model. Then we'll go into how orders are created, how they're combined, then we'll go into routing logic and how we track a metric for when food beats cart to the window. Towards the end of the presentation, we have a clip to watch of the model in action, as well as some of the outputs we typically use for analysis when running scenarios. So here we have a screenshot of a model we are using today. We have a single order board hiding in the back where orders are placed. We then have a handoff window that is a combiner where the order is handed off to the car. And then we have parking spots where cars will be sent to from the handoff window if the order is not ready. The model we're going to be walking you through today uses the priority of the entities as the ID for the combiner's matching conditions. So as cars are created, they are assigned an ID that all entities created from this ID can be matched when combined. For example, we have the vehicle called the parent 1 matched with bagged order member 1 in the handoff window combiner. So when orders are created, they could be routed to different stations. In this example shown, we have salads, burgers, and even some good-looking chicken on the flat top grill. The model has 2 production lines, one for drive-through orders and one for the front counter. Based on where the orders are being placed, the menu items created will either be produced on the drive-through side of the line or the front counter. The items will be routed to their respective station, whether it's a salad or a burger, and then there's a landing spot for the items to be expedited. Each item follows an assembly sequence shown on the right based on the revenue center. So the 10 wings will be routed to the input node of the hot hold station and sent to the parent input node of the combiner node named combined order. Once the food items are prepared and expedited, they are combined with either a tray or a bag that was created at the same time that the order was placed. Shown here, we have items ready to be run on a tray, meaning that it is for a front counter order, and we have a tray and a bag waiting for the food from its order. The bags waiting are in the parent input queue of a combiner, waiting for the food that belongs to the order. The bag and tray won't combine until all the items from the order are ready. Since different orders have different item counts, the model uses an integer variable of the bag entity that is assigned an order size when the order is created. So some bags have 2 items, other ones have 4 or 5, and that's what it'll be waiting for at this combined parent queue. Next, the food items and bags are matched using the priority or ID of both the bag entity and the food item entity. So order number 34 and food item number 34 are matched together. So once these orders are ready to go, they need to figure out where to go. The model uses routing logic, decision trees, and search processes to find that answer. First, we'll look at the handoff window and recall the combiner discussed earlier. As finished bagged orders enter the member input of the handoff window combiner, a search process is executed. What that search process is looking for is where the car is at that belongs to that bagged order that just arrived at the window. Cars are assigned using string variables to the different states depending on where the car is in the model, whether the car is at the order board or in the window queue, or if the car is at the window. A process with an assign that is executed when the car enters the order board input node, for example, is what updates the variable to the new state. So at each of these states, the variable is updated as it enters the new state. So why do we need to use the string state variable in the parking logic? Well, as Mr. Espinoza mentioned in his introduction, parking cars has become a more and more popular procedure for drive-through restaurants to handle exceptions to the rules, such as large orders or orders with outliers, and still maintain throughput at the drive-through. The following decision tree is commonly used in the restaurant world to decide when to park a car, starting with asking the simple question, if the car at the window's order is ready. If the answer is yes, you don't park the car. And if the order is not ready, the next question you want to ask is if there's a car in the window queue, followed by, is the order of the car in the window queue ready? If the last two questions answers are both yes, then the car at the window should be parked. In Simio, we can apply the decision tree logic to cars at the window. Using renege triggers, we can ask if there is a car in the handoff window queue, as well as if that car in the window queue has their order ready at the window. An integer state variable in the model called bag counter is assigned as bags arrive to the Windows member input node. When the bag arrives, a process is run that searches for the matching car to identify its status in the drive-thru. To do this, for two different entity types, the search syntax requires to be candidate.entity.priority for the bag to match with its car. Once the bag and the car are matched, a decide determines if the car in the model is in the queue, and if it's true, an assign increases the value of the integer state variable by 1. This is how the renege condition will know if the order of the car in the window queue is ready, and to park that car at the window by transferring to the renege node parked car path. This renege trigger is checked after a car has been at the window for 60, 90, and 120 seconds. This is the process used to track the state variable bag counter used in the renege condition. First, an assign creates a counter that will be used in the analysis to get a percentage of times food beats the car to the window. Then the search step matches the bag with the drive-thru order by priority or ID. Once the car is found, a decide asks if the car's string state variable, window or queue, is at the window. If that's a false and the car is in the queue, the next assign adds to the counter state variable bag counter that will be used that will be used for the parking car logic, and an integer state variable as well is increased by 1 to track the total number of times the food beats the car to the window. So now that the cars are parked, the orders still waiting for food at the expo station need to know whether they're going to be going to the window or to the parking lot. Here we have a screenshot of the expo station with orders that are ready and orders that are waiting for their food. So as the car is sent to be parked and enters the parked car combiner, a similar search step is run to find the order and assign the order a string state variable, a new identifier. So when the food is ready and combined, the order will be routed to the parking lot and not to the window. For the orders routed to the parking lot, a common scenario we test is who is responsible for transporting the order to the car in the parking lot. In this example, we have a front counter worker and a drive-thru worker. The worker assigned as the transporter will take the orders to the window or to the parking lot. Here we have a process for deciding the destination of the order. A decide step asks whether the bag state variable, window or parked, has been assigned to parked. If the state variable is not parked, the bag will be routed to the handoff window combiner. And if this is true, the bag will be routed to the parking lot by the set node step. We will now look at a short clip we recorded of the Simio model in action, starting with cars being generated based on a weighted distribution in a data table and a random table row referencing. The orders are placed and created in the kitchen in an order board behind the window. Cars then go to the parent input node of the handoff window where they will go, where they will get their order. Each time a car arrives at the handoff window, a timer starts of the renege trigger to decide whether to park the car at the window. So after a certain amount of time, the renege condition will check if there's a car in the window queue and if the car's order is ready. In this clip, the exception happens and a gray car is parked. So you'll see cars starting to stack up, and as a queue starts to form in the window, a gray car is parked. And as the gray car is parked, a transporter from the inside walks outside, hands off the order in a speedy fashion, drops off the order to the bag, returns to the front counter, and the car leaves the station. So once that transporter is called to carry the order to the parked car combiner, specifically the member input, where the parked car and the bagged order are matched and combined. For this model, the parked cars are routed to the front of the building, but one of the unique things Simio offers is we can change this location and distance from the expo station to test the impact of different parking spots, whether it's 40 feet, 50 feet, even 100 feet away, relatively fast. So the car leaves and data continues to be populated for our analysis. As Carlos discussed at the beginning of the presentation, drive-through optimization is becoming more critical as guest demands increase, and looking at one metric alone isn't sufficient anymore. Where the focus used to be on overall speed of service has now evolved into window times followed by throughput, and now the focus that the best in class are looking at is the rate that food beats the car to the window. All these variables are inputs in Simio that are analyzed to see the impact of different scenarios tested. So we can see how is the window time reacting to changes in the model, and then how does that affect throughput and food beating the car to the window. In this example, we show the impact of having variable window queue stacks from 4 to 5 to 6 in the queue, and then we tested that scenario at increasing volume levels. We look at these metrics to make recommendations on if the test supports further testing at the store level live, and to apply the assumptions or changes to the restaurant. All these metrics shown can look like improvements to the system, but more data is typically also looked at in parallel with these outputs to ensure that these metrics are not improving at the expense of other resources. The other resources tracked in our analysis are utilization of the workers and transporters, who's doing what and is responsible for processing the tasks. This is tracked as the work content over a period of time. So what percentage of time were the workers processing tasks, transporting, and working doing other things? In this example, we see in the green, we have that percentage shown, and we have on the top the idle levels, the levels that they were available to do other work. This can be expanded to looking at all resources across the board, such as resource utilization and par levels of materials on the line. The model looks at resource utilization to ensure that no production area is inhibiting the throughput of the kitchen. As well, we look at par levels to test the appropriate amount of food on the production line.
Yeah, the neat thing about Simio is there's a lot of data being generated as you saw the simulation go through. Main takeaway, it's not focused purely on speed of service without its impact on labor and resource and utilization. So the neat thing about this system is it allows you to track all these different data points to really understand how best to optimize your drive-through operations, whether it be a single lane drive-through, multiple lane drive-through, multiple parking spots, no parking. One of the things to keep in mind are all these data points that can be easily generated for you through a simulation model.
So with that being said, we'd want to thank Simio for having us today in the Simio Sync conference. We appreciate the opportunity to walk you through our model and some of the tools and how we use the different outputs and show it in our analysis.
And we are open for any questions that may come our way. Thank you so much and be well.
Phyllis and Victor, for the great presentation there. We've had some good questions here from the audience, really focused first on how the model was built and getting some more detail on that. So we'll start with those. First, this one, the animation of the restaurant looks great. How much effort was put into the animation, and was there anything that was difficult to animate?
Well, for the animation, we used a lot of the icons that were already in the Simio software, as well as some uploaded JPEGs and other to getting the framework of the restaurant, just so that we could, if we ever wanted to display it on a presentation, or just to make more sense of it, kind of like the visual aspect of that helps out a lot. Being able to see what the model's doing instead of because the outputs are going to be there regardless of whether you have an animated person walking to deliver the food or not. But it does help understand how the model's working using having this animation in there. But using the Simio's imported symbols, it was pretty straightforward and pretty easy.
Awesome. Great.
Yeah, we were able to do a lot of it using a third-party software where a lot of the 3D schematics that you see there, as Victor talked about, we built it in a third-party software and just were able to import it. And the most of the difficulty comes in the detail, making the cars turn at the appropriate time and shifting and making sure that the transporters don't run through a wall and such. But a lot of it comes through that third-party software where we're able to build it outside in a 3D drawing system and then import it through Simio's functionality.
Great, thank you for that. Still another one, still more on the how the model was built side. Can you talk about some of the data that was used to build the model? Even on kind of like the car arrivals or the orders, are they from forecasted information or historical information that you're feeding in?
Yeah, so we have historical information such as product mixes and deployment levels for different volumes. So we used that to guide us in our model so that we would know which orders would be likely to be generated so that we could replicate what is actually going on at the restaurant.
Great. Anything other
and just to add to that, and so we built this for a specific client, so our client was able to supply us with tons of information for us to be able to analyze and go through our normal statistical process to understand what is the best fit to model the reality of the data. So, behind the scenes of what Victor shared, that we were just focusing on this drive-through, there was a ton of data analysis that went in the background, right, to understand what is the proper distribution of time to produce a product in the kitchen, whether that be in one station or another. What are the inter-arrival times from counter versus drive-through? And so the client provided us, I want to say, Vic, about 3 months worth of product mix information and inter-arrival times that went through a whole ton of analysis before it got loaded into the model to understand what is best to mimic reality, as opposed to just using, point estimators and averages. It went through a whole plethora of analysis to understand what is the best fit for the different processes that are in the model. And of course, as you know, Simio allows us to put in whether it be a normal distribution, a Poisson distribution, whatever it may be, to again best match and mimic reality.
Yeah, and it was also something that we were able to use processes to not just say people are ordering, let's say the chicken or the burgers that we talked about. We were able to say if the person ordered a burger, what were the sides that would be accompanying that burger, and how many of the sides are typically accompanied with that burger. So we were really able to accurately represent what would be going on in the restaurant from that end.
Yeah, and additionally, one last thing to add to that, it's one of our arms of Profitality Labor Guru is the labor side. And so what we did for this client is we actually were able to go in and time how long it takes to load a basket, unload a basket, build the different products in the kitchen. And you heard Victor use the term work content. And so part of that study of building this model was understanding how much work is related to taking an order, building drinks, as I mentioned, producing and cooking product, And so that was also a long and arduous analysis to understand how much work is there truly behind creating any one of these products. And that adds to the work, move, idle productivity that Victor shares with you. So a lot of data analysis went into it. We can spend a whole half hour talking about all the different analysis that went in at different parts of the model. But I'll save you folks some of that and give you the gift of time back.
That's great. Thanks, Carlos. Thanks for the details there, guys. So we got another question here on model setup. You mentioned, once the order is complete, there's a different transporter depending on where the customer is. How did you set up the, appropriate transporter based on where the customer was located at that time, whether they were parked or, at the window?
So we used that search process to determine the location of where that customer was. And then through that, we would send the node or send the bagged orders to a server, and then from that server, it would request the specific transporter, whether it was whether the car was going to be parked or whether the car was going to be at the window. It would have a different transporter based on the server that's trying to seize that transporter and process the bagged item there.
Okay, great, awesome. So some of the questions that we have here are more around, kind of the restaurant processes and roles. So I just wanted to start off here. Is it possible to have, more than one car parked at a time? And is there model logic to account for that?
Yeah, more than one car could be parked at a time. And how we've done it before is that multiple bags could also be taken out at the same time if it's ready, and if the front counter or whoever the transporter is available for that to run the order to the car. So you could have multiple cars parked at the same time. The bags would be waiting at the server for the transporter to arrive and process the bags and then to deliver them. But definitely could have more than one car parked at a time if the scenario calls for it.
Great. Okay, well, I think that's all the time we have here. So again, just want to thank you all for the great presentation and for the Q&A here. We really appreciate you all being a part of SimioSync.
Thank you. We appreciate you guys as well.
Thank you very much, Ryan. Be well, everyone.
This concludes this presentation. Please click on the back button to access the next presentation.